Warm welcome to all. My name is Balaji babu. I belong to Department of Chemical Engineering. My project is intensification of thermal energy storage in phase change materials using silicon dioxide nanoparticle. My guide is Dr. T. Srinivas. Background of the project. I have used phase change materials. What phase change materials actually means is that it has enormous amount of heat, enormous amount of ability to store heat and emanate heat whenever it undergoes phase transformation from liquid to solid. So this can be incorporated in industries where there is a need for heating application. So I have used three nano-PCMs such as sodium thiosulfate pentahydrate, paraffin wax, zinc nitrate hexahydrate by incorporating different concentration of silicon dioxide nanoparticle. So here I have used silicon dioxide nanoparticle as an enhancing element. Objectives: to intensify the thermal energy storage of PCM, usage of silicon dioxide nanoparticle to showcase the improvement in heat storage capacity of PCMs. Literature review. So this literature review I have done to justify as to why I went for these three nanoparticles and also these three nano PCMs with silicon dioxide as a special nanoparticle. And Omum Wait has conducted and showed that usage of nano PCM is efficient than usage of plain PCM in various processes wherein the heating is required. And in the second experiment, which is conducted by Manilia and Jain, addition of silicon dioxide nanoparticle to the PCM increases the latent heat of fusion. So that is why I went for silicon dioxide nanoparticle. Here, the properties of phase change materials, a study of paraffin. So study is conducted and paraffin is found to be safe, non-corrosive and chemically stable. So these features of paraffin wax that made me to choose paraffin wax of as one of the three nano PCMs. And solar desalination. In solar desalination process, sodium thiosulfate pentahydrate portrayed high latent heat of fusion per unit volume. So this is the prime reason why I went for sodium thiosulfate pentahydrate. It exhibited paramount amount of heat, latent heat of fusion. And the final one is comparative study of organic and inorganic PCMs to ascertain high thermal conductivity. Here, inorganic salt zinc nitrate hexahydrate has much value of thermal conductivity. That is why it is chosen. Materials required: sodium thiosulfate pentahydrate, paraffin wax, and zinc nitrate hexahydrate. These three nano PCMs. Nanoparticle is silicon dioxide. Instruments that I have used are thermoanalyzer, ultrasonicator, and water bath. Thermophysical properties of materials is furnished here. So for silicon dioxide and for the other three PCMs, the physical properties are mentioned here. Methodology. Here the thermal conductivity is measured for these three PCMs. Ultrasonicator is used as a source of heating and water bath is used as a source of cooling. At different temperature, the thermal conductivity for these three nanoparticles, the nano PCMs coupled with the silicon dioxide particle, is measured. So at the right side we have one image where one can easily see that these three samples are filled in a borosilicate glass up to the brim. So here the weight of the sample varies, which clearly implies that zinc nitrate hexahydrate with 60.6 grams has higher density than other two nano PCMs. This is the experimental setup. At right side we have the samples and this is the thermoanalyzer. At the left side we have thermoanalyzer connected with the sample. Here this is the ultrasonicator, which is used as a source of heating. The thermal conductivity is measured at specific temperature, which is maintained by the ultrasonicator, uh, with a sample consisting of uh, the PCMs, nano-PCM, at different concentration. So here thermal conductivity is measured at 8 different temperature with an interval of 5 degrees centigrade from 30 degree to 65 degree for sodium thiosulfate pentahydrate, and 20 to 55 and 35 to 65 for zinc nitrate hexahydrate and paraffin wax respectively. So why does the temperature criteria varies for these three nano PCMs is that it is fixed based on the melting point of the nano PCM. Four readings before the melting point and 4 reading after the melting point. So it is just basically the solid and liquid. So when it solidifies, that is taken as a different sector, and when it liquefies, that is taken as a different sector. That is why the split is here incorporated. Results and discussion. Effective thermal conductivity of silicon dioxide paraffin wax nano PCM, and for other two nano PCM, the results are discussed in the upcoming slides. Effective thermal conductivity of silicon dioxide paraffin wax nano PCM. Here the thermal conductivity is measured from 35 to 65 using different concentration of silicon dioxide nanoparticle. So that forms a nano PCM. The concentration, the volume fractions are 2%, 4%, 6%, 8% and 10% using a thermal analyzer, and these experiments are repeated two more times, and also whenever the repetition is done, 3 values are considered. So almost 6 times it is done. So the upcoming figures shows the results for effective thermal conductivity. The effective thermal conductivity is nothing but thermal conductivity of nano PCM divided by thermal conductivity of base PCM. So this is it is easy to infer when we first look at the graphs and come back to this slide. So here effective thermal conductivity is on y-axis and concentration of silicon dioxide nanoparticle is in x-axis. At different concentration, thermal conductivity is measured at constant temperature of 35 degree in the first graph. For example, let me explain how I calculated the thermal conductivity. Let's say we are calculating the effective thermal conductivity at 0.03. Here thermal conductivity of base of nano PCM at 3%. So that is so 3% is not taken into consideration as we calculated only for 2, 4, 6, 8, 10. So I am going with 4%. Thermal conductivity of silicon dioxide paraffin wax nano PCM at 35 temperature is measured for 4% silicon dioxide concentration. That is 4% silicon dioxide concentration divided by base PCM. Base PCM doesn't have any silicon dioxide nanoparticle. So the variation from base PCM to the PCM with certain amount of concentration, that is exhibited in this graph, and as the graph is positive, the effective thermal conductivity keeps increasing with concentration. That is what the inference which is drawn from this graph, and it is also same for the upcoming graphs at different temperature. This is calculated at 35 degree and next graph is 40 and so on and so forth. 45 degree is also the graph is positive. For 50 degree is also the graph is positive, and it is positive till 65 degree. So the conclusion that is drawn from this graph is here the temperature and concentration of nanofluid increases, the enhancement is found to be more. So here I have shown only the concentration, and the effective thermal conductivity keeps increasing with increase in concentration. So that is the portrayal of enhancement. Here enhancement in the effective thermal conductivity is in the range of 2.5 to 13.7%. Here, yes, this enhancement is high for 13.7%, which is observed at 65 degree centigrade nano-PCM temperature and 10% concentration. So this indicates that this is the highest volume fraction concentration that I used, which is 10%, and also this is the highest temperature, 65. At higher temperature and at higher concentration, enhancement is found to be more for silicon dioxide paraffin wax nano-PCM. Going on to the next part, we have effect of temperature. Earlier it was effect of concentration, and now this is the effect of temperature on thermal conductivity of silicon dioxide nano-PCM. Here also the temperature is calculated. The temperature 35 degree to 65 degree, 30 to 65, and effective thermal conductivity is calculated in the same manner. For example, let's say at 50 I am calculating the effective thermal conductivity, which is thermal conductivity of silicon dioxide nano PCM at 0.02, that is 2% concentration, divided by the nanoparticle silicon dioxide paraffin wax nano PCM at 30 degree. So here the variation is taken as the temperature, that is thermal conductivity of the nano PCM at 50 degree divided by thermal conductivity of PCM at 30 degree. So how it varies from 30 degree, how it varies for upcoming increasing temperatures. So here also the all graphs are showing positive variations till this 10% volume fraction. Here the volume fraction is fixed as a constant and temperature as a variance with respect to effective thermal conductivity. So the inference drawn from these portrayal of results from the graph is that effective thermal conductivity improves from 2.5 to 4.6% for silicon dioxide nano PCM. The highest enhancement was found to be 4.6%, which is observed at 65 degrees centigrade, and for the 10% of volume fraction of nano PCM. So here one can patently look into the results that is drawn from for the temperature effect, and also the concentration effect is more profound. It is more profound than the results that we obtain for temperature. That is why the increasing concentration gives more enhancement than increasing temperature. So it is better, the concentration, if it is increased, the results are better. Coming on to the second nanoparticle, zinc nitride hexahydrate nano PCM. So here the range varies from 20 degree to 55 degree, and the volume fractions are remaining the same, 2%, 4%, 6% till 10%. The effect of nanoparticle concentration. So similar whatever the process which is done for the silicon dioxide nano PCM in the initial stage, it resembles the other two nano PCM, also resembles the same results, but comparing these three PCMs at the end, that'll form the conclusion. Let's look into this current slide. Here zinc nitrate is measured, the thermal conductivity is measured against the concentration of zinc nitrate nano-PCM. So this is the inference. Let's get in the graph first. So this is the graph we have, and here it is also similar to what I have done in nano-PCM, paraffin wax nano-PCM. Here concentration of silicon dioxide nanoparticle, volume fraction is taken in x-axis, and effective thermal conductivity is in y-axis. For example, let's say I am going to measure the effective thermal conductivity at 6%. So here is a 6%, and the temperature is constant here. So the effective thermal conductivity is measured in this way, which is thermal conductivity at 0.06, that is 6%, divided by thermal conductivity at 0%. 0% implies that there is no presence of silicon dioxide nanoparticle. So this will give the effective thermal conductivity, and here the effective thermal conductivity is found to be positive for all the temperatures ranging from 20 to 55. So here is the conclusion. Increasing the concentration of nanofluid. So here also the concentration of nanofluid has more profound effect than increasing the temperature, and the effect of temperature will be looked in the upcoming slides. The variation is from 1.6 to 9% for zinc nitrate hexahydrate nano-PCM. The highest was 9% observed at 55 degrees centigrade fluid temperature and 10% volume fraction. So here it is pertinent to note that this 55 degree centigrade is the highest temperature wherein the test is subjected for silicon dioxide zinc nitrate nano-PCM, and 10% is the highest volume fraction. So here also it resembles the earlier conclusion, that is at highest concentration and highest temperature within the ambit of this experiment, the enhancement factor is more. Going on to the next topic, which is effect of temperature on thermal conductivity. Here the temperature is kept as a varying parameter and at constant volume. The temperature, and here also the effective thermal conductivity is measured in this way. Let's say I am going to measure effective thermal conductivity at 40 degree. So thermal conductivity at 40 degree of silicon dioxide zinc nitrate nano-PCM divided by thermal conductivity at 20. So it is the thermal conductivity at subsequent temperatures divided by thermal conductivity at the initial temperature. So that is how the graph is drawn, and all the graph portrays the positive trend. Jumping on to the conclusion, so enhancement in this effective thermal conductivity is in range of 8.1 to 8.4. This is the enhancement that we observed, and the highest enhancement was 8.4, which is obvious because the highest temperature is 55 degree centigrade, and 10% volume fraction is used. So this also resembles the earlier PCM's results, which is at higher temperature and at higher concentration the enhancement factor is more. So the final PCM is sodium thiosulfate pentahydrate nano-PCM. Here the measurements are from 30 degree to 65 degree, and the concentration remaining the same from 2% to 10%. So this is the conclusion. And here initially the nanoparticle concentration effect on thermal conductivity of silicon dioxide, sodium thiosulfate pentahydride nano-PCM is shown. So this is the inference. Going on to the graphs, similar it is also similar to the previous two PCMs. The trend is positive, and in an arbitrary manner, let's look into the graph at 45 degrees centigrade, that is right side this graph. Here the effective thermal conductivity is calculated in this manner, that is thermal conductivity, let's say at 8%, thermal conductivity of sodium thiosulfate nano-PCM at 8% divided by thermal conductivity at 0%. That will give us effective thermal conductivity. And similarly, the graph is drawn. The effective thermal conductivity just means that the variance from the PCM with no silicon dioxide nanoparticle. So from 0 to here 8%. So from 0 to 8%, that is the variance. From 0 to 2%, from 0 to 6%, that is how effective thermal conductivity is calculated, and it is plotted against concentration of silicon dioxide nanoparticle. Here also the trend that we observe is positive, there is no declination. So this is the inference that I drew from the results that I obtained. Here the enhancement ranges from 1.57 to 10.5 for silicon dioxide, sodium thiosulfate pentahydride nano-PCM. The highest enhancement was observed at 10.5 at 65 degrees centigrade, which is 10.5%, and at 10% volume fraction. So this is also patent, and it is intelligible as the highest temperature and highest volume concentration renders as the maximum enhancement. This is effect of the temperature on thermal conductivity of silicon dioxide, sodium thiosulfate pentahydride nano-PCM. So here the temperature is kept as a varying factor and the concentration remains constant. The temperature varies. So here the trend is totally positive. So the effective thermal conductivity, let's say at 60 degree, is calculated in this way. Thermal conductivity at 60 degree divided by thermal conductivity at 30 degree. That is how the graph is plotted. Again, we have positive trends for different volumes till 10% from 2%. So this is the conclusion that is drawn for this. The enhancement range varies between 1.57 to 10.5 for sodium thiosulfate pentahydride nano-PCM. The highest enhancement is 10.5, which is observed at the highest temperature that the nano-PCM is subjected to the process, which is 65 degrees centigrade, and at the highest concentration that the nano-PCM possessed, which is 10%. So coming on to the conclusion. So what I did in conclusion is these three nanoparticles results were combined, and the conclusion is drawn from the combination of results of these three nanoparticles. So here the concentration varies from 2% to 10%, and effective thermal conductivity increases with increase in concentration, as well as the enhancement also increases with increase in concentration, and increase in temperature also yields highest enhancement. But it has to be noted significantly that increasing concentration has much profound effect than increasing temperature. That is why the highest concentration has rendered high enhancement factors. So here, for a given nanofluid, effective thermal conductivity increases proportionally with concentration and temperature. The enhancement is more for concentration, that we noted in all these three nano-PCMs that we have seen in previous slides. For silicon dioxide paraffin wax nano-PCM, the effective thermal conductivity is increased by 13.7% when compared to the reference material. The reference material is the base PCM without any trace of silicon dioxide nanoparticle. And again, for zinc nitride hexahydrate nano-PCM, the improvement is 9% more than the reference material. And also for final one, which is sodium thiosulfide pentahydrate, the improvement is 10.5% when compared to the reference material. So here one can easily note that silicon dioxide paraffin wax nano-PCM has given the maximum enhancement of 13.7%. So this is the maximum enhancement, and which is followed by sodium thiosulfide pentahydrate, which provided 10.5%, and finally the zinc nitrate hexahydrate, which is 9%. So what I conclude from this is that using silicon dioxide and paraffin wax nano-PCM at higher concentration will give us maximum the enhancement factor. So that is to be used in industries when they have these options. So within this ambit of experiment that I have conducted, silicon dioxide paraffin wax nano-PCM shows the highest enhancement factor. Future work. So this three nano-PCMs that I chose are silicon dioxide nanoparticle, and the nano-PCMs are zinc nitrate hexahydrate, sodium thiosulfate pentahydrate, and paraffin wax. The experiments that I did are separately on these three nano-PCMs, but what one can do is it can also carry it out in a blended manner, which is the three nano-PCMs can be blended and the hybrid nanomaterials can be formed, and the experiments can be carried out. Also, the effect of nano-PCMs PCM thermal conductivity on charging and discharging of nano-PCM can be investigated, which is charging of heat and discharging of heat of nano-PCMs can also be investigated additional to the process using hybrid nanomaterials. Thank you.